morning. Today we shall see how to use the supplementary codes given in this material. One Neumann Stability Analysis for multi-level, multi-step methods. When I was going through the literature, so I found there is a lack of clarity in implementing the one Neumann Stability Analysis or approximate dispersion relation analysis for multi-level, multi-step methods. So I went through plenty of literature. I found there is a problem in the numerical gain or dispersion relation what they have implemented for this thing. So if you know any correct manuscript which implemented the one-image stability analysis or approximate dispersion relation analysis for multi-level, multi-step method, please inform me in the comment section. Now we shall go to the code. So in this paper we have provided plenty of numerical gains for different schemes. So this is a SSP-RK3 schemes numerical gain. What we'll do in this video is we will compare this theoretical prediction with the actual numerical prediction, whether they are matching or not. So like that we will be doing for this method and Adam-Bashort methods. So now we shall dive into the code. So if you go to that supplementary material, you can find the link here. You can right click and open it here. So it will redirect to my GitHub page. You can download the code here. So we shall extract this. So we shall copy the path so that we can use it in MATLAB. Now I have copied the path here. So we are in the directory. The simplest code is FTBS scheme, that is forward in time and backward in space. We shall open the code. So this is a live MATLAB script similar to Jupyter Pi notebook that we use in Python. So here we are solving the one-dimensional linear convection equation. So when we discretize this using forward in time and backward in space, this is what we are getting. And if you apply the Fourier Laplace transform, we get the numerical gain. So I hope you are aware of this one. The numerical gain of FTBS scheme is 1 minus CFL and this expression. So we shall test whether we are getting this numerical gain from the simulation. So these are the standard MATLAB command to clear screen, and this is to clear all the variables in the working directory, and this is to close all the windows. So this is the length of the domain. We are assuming B sin x initial condition with wave number 1. We are splitting the domain into 101 grid points. So we know here we are applying the periodic boundary condition. We know we should apply the periodic boundary condition for one Neumann stability analysis. So we know y of 2 pi is equal to sine of 0. So we want to delete that unnecessary point. That's why we are deleting the lost point. And we are calculating dx. So here our float time is 5 seconds and signal velocity is 1. We are using CFL number 0.5. From the CFL number, we are calculating the del t, time step. From the time step, we are calculating the number of time step using this command. So this is the time loop, and we are storing the first initial condition here, and this is the step where we are calculating the derivative. So this is a function that's here. Here you can find we are using suck shift command to calculate the derivative. So what this command does is pretty straightforward. Let's define one variable a is equal to 1:5. So this will create a array from 0 to 5 if we use suck shift command. Suck shift of a, here I have used 0, 1. So you can notice that it has shifted this index. So it starts from 0 to 0 and ends at 5. When we use suck shift 0, 1, it has moved this lost variable to the first variable, first index. That's what we have done. So that we can easily calculate the derivative without using loop. Python or MATLAB, we should try to avoid loop as much as possible. That's why we are using this syntax. and we are also using the advantage of periodic boundary condition. So this we have completed. So this is a simple FTBS implementation, and here we are calculating the time level. And this is exact solution. These are just plotting commands. Here we are calculating first Fourier transform of the signal at that current time step. Here we are calculating the dominant frequency. So what's the dominant frequency? And we are storing it on at every time step. So it's a spatial FFT. It's not a temporal FFT where we will store one variable at a particular point at every time step. Here we are storing all the spatial variable at one particular time and calculating the FFT. We know that in Neumann Stability Analysis, we should the numerical amplification factor is calculated by the ratio of current FFT and a previous FFT. That's what we are doing here, and we are printing that. So this is a theoretical amplification factor implementation that you can refer the paper. And here we are printing that amplification factor. Let's run the code. So this is a animation of the result. So this is a numerical amplification from the simulation. This one. So this is FFT is calculated from the simulated result, and we are calculating the numerical gain. So in this step, we are implementing the theoretical amplification factor. Both are exactly matching. Now we shall move to the next code. We have seen how to implement the FTBS scheme and how to cross-check the numerical simulation with the theoretical gain what we have presented in the paper for FTBS scheme. There is no difference between the standard Neumann Stability Analysis and the analysis what we present here for FTBS scheme. The problem comes only when we use a multi-level multi-step method. The easiest multi-step method that we have implemented here is SSPRK3 method, and for the spatial discretization we have used L2R1 scheme. That means we have used 2 point left side and 1 point right side. That's why we are denoting it L2R1. So this is a pretty straightforward implementation of SSPRK3 L2R1. So when we apply the Fourier decomposition, we'll be getting this expression. The first expression is almost similar to the standard Fourier expression or one-Neumann stability analysis what we use. The second expression, please a little bit care, because in the second step we are using u of first level here, and here we are using u of zeroth level. So we should implement the corresponding time level here. So that's why we are having u tilde 1 here and u tilde 1 another expression, and here we are having u naught. So this whole expression should come here. This whole expression should come here. And in the third time level, this is the expression. So this is u naught, and here we should substitute u2 here. This whole expression. So this is how it works. And calculating numerical gain is pretty straightforward. If we divide this and this, we'll be getting numerical gain at different time steps. And this numerical time steps, this first numerical gain should come here. This one. This expression. Sorry. This expression should come here. And once we calculated this second gain, to calculate the final gain, we should substitute that value here. I hope you got a little bit idea how to implement this numerical gain for Runge-Kutta method. Similarly, you can apply for any Runge-Kutta method which you like. So we already saw in FTBS discretization these codes. So now we shall directly go to the Runge-Kutta method implementation part. So here we are calculating the derivative using the u naught time level, and then we are matching the little time advancement given in the first time level implement in Runge-Kutta method. Using that value, we will be calculating derivative, Again, we are going to the next time level of Rangikuta method. Still, we didn't complete we didn't go to n+1 level, the local time step. Time advancement we using Rangikuta method. So then we are again going to the third time level. So here we are going to the final time level. So this is exact solution. Now we shall compare our simulation results. So let's run this section. So this is a simulation result and exact solution comparison. Both are almost exactly matching. So here this gives a numerical amplification factor using FFT commands. So you can find both of them are same. So that's why we have validated our scheme. Now we shall go to the third one, the Adam backward and backward in scheme. This is slightly more trickier compared to the previous one because it has corrector and predictor step. In addition to that, Adam backward method has two numerical gain. So this is a standard implementation of Adam backward scheme for a linear convection equation. And when we apply the von Neumann stability analysis, this is what we get. So here you can notice that we'll be getting two gain values because it's a second order equation, second order polynomials kind of equation. So we'll be getting two gain. So using this expression, we can calculate. Once we got the gain value here, we should substitute that in this second expression to get that final gain. So this we already saw. So this is the standard implementation of Adam backward method. Now we shall see how to calculate the exact gain. So we have defined two dummy variables because we already use a KH and CFL number in our code. That's why we are using KH1 CFL number to calculate the exact and this gain, exact numerical gain. So this is G1 expression. This is the expression. This one. This G1 expression. So we should find that two numerical gain. That's why we are using solve command to get it. So these are the roots of Adam backward scheme. So once we found this G1, we should substitute that in the final amplification factor. That is a corrector step amplification factor, this one. So that will write 2 numerical gain. These are the expression for G1 and G2. This expression I have typed here. Now we shall run the code. This is a comparison between Adam backward method and exact solution. This is the numerical amplification factor from the simulation, and this is a numerical amplification from the theory. So we have two gain. You can notice that first gain is matching and second gain is not matching. That means first gain is physical and second numerical amplification factor is not physical. I hope you got an idea how to implement the von Neumann stability analysis for a multi-level multi-step method. This is pretty much straightforward. So if you want to give this kind of assignment for student, you can do it. If you want to implement this kind of analysis for any of your method you like to wish, you may contact me through my mail ID or through message. Thank you for watching.